Hi, I'm Thomas Sibyl, and today I'm going to give you an overview of our work on extreme value theory, with a particular focus on its application to extreme winds in different regions of the United States. Firstly, we examine the limit distribution, exploring the Weibull, Fréchet, and Gumbel laws, which are fundamental for understanding extreme weather events. Then we introduced the generalized extreme value distribution, which provides a unified way to model these phenomena. To visually identify the most suitable distribution type for our data, we explored graphical methods. Then we delve into the parametric and non-parametric estimators of the shape parameter Xi, such as the Pickens, Deckers, Einmal, and Hahn estimators, as well as the Hill estimator, which are essential for fitting our models to observed data. Subsequently, we focused on evaluating the distribution above a certain critical threshold. For this, we introduced the generalized Pareto distribution and the mean threshold exceeding function, highlighting its characteristics and important consideration for parameter estimation and threshold selection. Our study provides an in-depth understanding of key concepts in extreme value theory and their practical application to the analysis of extreme winds. This knowledge is essential for assessing risks and making informed decisions in disaster management. Additionally, we then applied extreme value theory to extreme winds in the USA as a practical case study.
Hello, my name is Yun Flatres. I'm going to present you the application part of our TER. Violent winds in the United States pose significant risks to infrastructure and communities. Our analysis, based on data obtained from NOAA, National Climate Data Center, sheds light on the frequency, intensity, and geographical distribution of these extreme events, providing crucial insight for risk management and resilience planning. The data were sorted in descending order to facilitate the analysis of extreme events. We first counted the number of extreme events per state and created a bar plot to visualize the distribution. This analysis helps in identifying the states most affected by extreme events. We then examine the most affected states for each year by aggregating the data and selecting the state with the highest number of extreme events. This analysis provides insights into the temporal variability of extreme events across different states. We can see that Texas is the most affected state. Next, we analyzed the maximum and average magnitude of events over the years. Two line plots were created to visualize the trends in maximum and average magnitudes. This analysis helps us to understand the intensity of extreme events over time. We aggregated the data to calculate the sum of property damages for each year and created a histogram to visualize the distribution. We find that the year 2020 was the most impacted by these extreme events. Further, we conducted a detailed analysis for the year 2020, including the total number of extreme events, the most common event types, and the states most affected. While the magnitude of weather events may impact the damages incurred, various factors like geographical location, population density, and infrastructure also play a significant role in determining the extent of the damage. Therefore, an accurate assessment of risks requires a comprehensive analysis of multiple variables.
Hi, my name is Antoine Bonnefond, and I'm going to present you the next analysis and the several extreme charts. The code we've developed encompasses several statistical estimations and analyses aimed at understanding extreme events related to property damages. So I will present you our approach. First, I will talk about tail of distribution. What is it? Tail of distribution, often associated with extreme value theory, characterizes the behavior of rare but significant events in a dataset. Understanding the tail of distribution helps us to model and predict extreme events such as severe storms or natural disasters, providing valuable insights for risk assessment and management. In our analysis, studying the tail of distribution allows us to identify the most extreme events and assess their potential impact, aiding the development of effective mitigation strategies. We conducted mean excess analysis, which focuses on the average excess over a threshold. This analysis helps in estimating the tail behavior more precisely. By performing linear regression on the stable part of the mean excess graph, we identified the threshold value and computed estimators for further analysis. Then I will talk about determination of various estimators. We will see values of estimators, calculation of Xi, and determination of the law. We began by calculating three non-parametric estimators, Picans, Hill, and Decker's estimators. These estimators helps us to understand the tail behavior of the distribution of property damages. For each estimator, we plotted the values against selected proportions of the highest values. This analysis allows us to assess which estimators best fits our data. Our findings suggest that the tail behavior of property damage distribution follows the Fréchet distribution, indicating heavy-tailed behavior. We determined the tail index using Hill's method and further verified it with the POT method. The estimated parameters provide valuable insights for risk assessment and modeling of extreme events, essential for decision-making in various sectors. Through this statistical analysis, we've gained a deeper understanding of extreme property damage events, facilitating better risk management strategies and decision-making processes.
As a conclusion, our analysis has provided valuable insights into the dynamics of extreme events and their impacts. We've observed significant variation in frequency, intensity, and economic consequences across states and years. By understanding these patterns, we can better prepare for and mitigate the risks associated with extreme weather phenomena. Moving forward, proactive risk management and resilience building efforts are essential for safeguarding communities against the increasing threats posed by extreme events.